So having said that, let's jump back into the lecture. Minimize. Screen share. All right. So because implicit differentiation is one of those things that it's hard to wrap your head around at first, I think we should go through a couple different problems here. This is not, oh, that was an ugly sound. This is not an immediately obvious concept. Me personally, this was the hardest thing to get my head wrapped around when I took calculus. In fact, it was almost the end of the semester when I finally was like, oh, that's what that was? And even then, it took me probably till Calc 3 to really, truly appreciate what this was trying to tell us. This is just a really weird concept. All right, so what we're trying to do is we want to find dy dx. And we're told that y cubed plus y squared minus 5y minus x squared is equal to -4. So the first thing we want to do, apply the derivative to both sides. D dx of y cubed plus y squared minus 5y minus x squared is equal to the derivative of a constant. That's just 0. So let's go ahead and put in 0. Let's not even bother writing it out. Just go straight to 0. Right now this we know can be rewritten now as d dx of y cubed plus d dx of y squared minus 5 times d dx of y minus d dx of x squared. All of this is equal to 0. Well, we're going to need to apply the chain rule here, 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 and here, right? And we're going to need to apply implicit differentiation here. Implicit differentiation, chain rule, plus implicit differentiation, chain rule, plus implicit differentiation. So this is going to come out to be d dx, my mistake, d dy of y cubed times d dx of y plus d dy of y squared times d dx of y minus 5 times dy dx minus d dx of x squared is just 2x. All of that is equal to 0. Now notice this d dx of y, these are dy dx's. Cool. This d dy of y cubed, this thing's going to end up being 3y squared times d dx of y is dy dx. I'm going to write that in black. Plus d dy of y squared, that's just 2y, times dy dx minus 5 times dy dx minus 2x. Everybody agree? Folks at home, do we agree thus far?
Yeah.
All that's equal to 0. Can't forget that. All right. Now notice what this means then is we can factor out this dy dx term, right? So let's go ahead and do that. We're going to have dy dx times 3y squared plus 2y minus 5 minus 2x is equal to 0. Well, we can add 2x to both sides. So dy dx times, let me actually write this slightly different. The polynomial 3y squared plus 2y minus 5 times dy dx is equal to 2x. Now all we have to do is divide this polynomial from both sides to get that dy dx is equal to 2x divided by 3y squared plus 2y minus 5. Now notice something here. The reason why this is called implicit differentiation is because first, coming back to the original function, there was no easy way of writing this to get just straight up dx or dy dx. We were going to have to apply chain rule no matter what we did. Okay, that's the first thing. The second thing is that when we get to dy dx, we can't actually separate it out as a function of x. Instead, we have a function of x and y. And this is what implicit differentiation is all about, is finding these tricks, these mechanisms of solving for derivatives, even in terms of y and x, when it's not immediately obvious. We know y is a function of x, we just don't know a nice, easy way to write it. We do know that the equation is the relationship between the two, well, it defines or describes the relationship between the two, and then we can apply chain rule to get a bunch of dy dx's out, and then we can solve for those dy dx's to get what that derivative is in terms of x and y. This is, again, what implicit differentiation is all about. It's just an application of chain rule. So really quickly to look at what all of this looks like, this is what the function, the equation that we just took the derivative of, this is what it looks like. Notice this thing is not a function, right? It fails the vertical line test several times. Excuse me. So we can't really write it in a nice form, but we can still get the derivative as a function of x and y, or rather as an equation of x and y, I should say. Going through the steps, exact same thing. Start off with our original equation, apply the derivative to both sides. Hey, check it out. After we apply implicit differentiation, so the chain rule with those implicit derivatives of dy dx, all of a sudden we get a bunch of dy dx's that we can factor out. We push that 2x to the other side, factor out that dy dx, get that polynomial. We divide that polynomial from both sides. So now, if we wanted to find the derivative at any point, all we need to do is find out what x and y are. That's it. Once we find out what x and y are, we can go back to our derivative, plug those in. Bada bing, bada boom, you got the slope of your tangent line. Does this make sense to everyone? Now I want to make a point of what this implicit derivative really is. This implicit derivative is this dy dx term here, here, and here. We can't actually define dy dx directly. We don't have a way of doing that. Not without some rearrangements. And that's why this is called an implicit derivative, is you can't really start off by saying, oh yeah, y is equal to this, so this is dy dx. No. You're gonna have to go through, say, I don't know what this dy dx term is, but whatever it is, I know that it has to abide by this relation, because I just applied the derivative to both sides and got this relation. Well, hey, this lets me now solve for dy dx. So the entire process is implicit differentiation. But this dy dx term here is the implicit derivative. Cool? Cool. So, having said that, I'm going to let y'all play with this problem for about 5 minutes. I'd like y'all to take a look at it. See if you can figure it out on your own. We're going to work it out together after that. Always reminds me of an hour class. I don't see the exterior, I just see the interior of it for whatever reason. Or Kirby hugging something. Yeah, I just made a video game reference, everybody. What's up? I'm cool. All right. So who thinks they have it solved? Folks at home, anyone? All right, well, since it doesn't appear anybody did, let's work this out. So up on the board, I've gotten this worked out to take that implicit derivative with respect to y squared, right? What we know is that we can apply the chain rule here. So we get 4x minus d dy of y squared times the implicit derivative of y with respect to x. All this is equal to 0. Now, from here, we've got 4x minus dy, d dy of y squared. That's going to end up being 2y times dy dx is equal to 0. Well, this tells us then that if we subtract 4x from both sides, negative 2y times the implicit derivative of y with respect to x is equal to negative 4x dividing negative 2y from both sides. This tells us that dy dx is equal to 4x over 2y, or 2 times x over y. So if we want to find the slope of this tangent line here, the line tangent to our equation at the point 1, 1, we would just apply the point 1, 1 into this. So dy dx at 1, 1 is equal to 2 times 1 over 1. It's just equal to 2. Just for the folks at home, I've used this notation a lot with a bar behind a thing. This just means you're holding something to be true. In our case, we're holding that xy is equal to the point 1, 1. That's all it means. We're going to see later in the semester another similar form of notation. It's going to indicate something similar. But looking at our problem and their solution, starting off with 2x squared minus y squared is equal to 1. Take the derivative of both sides. Well, this 1, it's going to have a derivative of 0. 2x squared differentiated with respect to x, well, that's straightforward. That's 4x minus, this is where we're going to have to take the implicit derivative. We're going to have the chain rule and that implicit derivative, right? So then we're going to say, cool, subtract 4x from both sides, divide out that negative 2y. Now we want to find the slope at the point 1, 1, or the slope of the tangent line at the point 1, 1. Plug in 1, 1, bada bing, bada boom. You get a tangent line that's equal to 2, or a tangent line with a slope of 2. Okay. Now let's say we're given a demand function. Again, this is business calc, so we're working with a business, right? We're given this demand function. We want to find the rate of change of the demand x with respect to price p when x is equal to 100. What are we going to do here? So what we're trying to find is dx dp, not dp dx. If we took the derivative right now, it would be dp dx, right? That's not what we want. We want dx dp. So what are we going to do? Well, we could multiply both sides by that polynomial. Since this thing will never be 0, right? It'll get really close to 0, but it won't be 0. Actually, it won't even get close to 0, it'll just get to 1. So let's multiply both sides by that polynomial. First, we want that. What we have is p times that polynomial, which is 0. Oh, I hate these small decimals. 0, 0, 0, 0, 0, 1, x to the third, plus 0.01 x plus 1 times p is equal to 3. Now we're going to differentiate everything with respect to p. ddp of, that was 1, 2, 3, 4, 5, 10 to the negative fifth times x to the third plus 10 to the negative second times x plus 1 times p is equal to, differentiating 3 with respect to p, it's going to be 0, right? Well, now we're going to have to apply the product rule. First, before anybody gets confused, all I did here was convert our decimals into powers of 10. I personally hate decimals like this, so I usually try to convert them if I can. And for the sake of cleaning up the board, I thought it would be better to write it this way. But here, like I started to say, we're going to have to apply the chain rule. The product rule. We've got one function, and we've got another function, right? P can be thought of as f of x, and then this polynomial can be thought of as like g of x. So bringing this over, I guess in this case they would be g of p and f of p. But bringing this over, we're going to have d. Let me actually write this slightly different with multiple colors so that everything's obvious. First, we're going to have p times the derivative with respect to p of 10 to the negative fifth times x cubed plus 10 to the negative second times x plus 1 plus 10 to the negative fifth x cubed plus 10 to the negative second x plus 1 d dp of 1 is equal to 0. So this is going to come out to be p times we can break this up using sudden difference rule and bring out these constants. So this is going to be p times d, my mistake, 10 to the negative fifth, d dx ddp of x cubed plus 10 to the negative second d dp of x plus d dp of 1, which is 0. That's going to disappear in a minute, right? Plus 10 to the negative fifth x cubed plus 10 to the negative second x plus 1. Well, the derivative, my mistake, I made a typo up here. This should have been p. The derivative of p with respect to p is just 1. So that's all we're left with, right? Now this thing, we're going to have to apply implicit differentiation here, here, and this is going to be equal to 0 here. So we get p times 10 to the negative fifth d dx of x cubed times d x dp plus 10 to the negative second. This is going to be d x dp, close that, plus that polynomial, 10 to the negative fifth x cubed plus 10 to the negative second x plus 1 is all equal to 0. So we have p times 10 to the negative fifth x cubed differentiated with respect to x is just going to be 3x squared. Dx dp plus 10 to the negative second dx dp plus this crazy polynomial, which we're actually just going to go ahead and subtract from both sides. Negative 10 to the negative fifth x cubed plus 10 to the negative second x plus 1. Right, so all I did here at the very end was subtract this polynomial for both sides. Notice now we can factor out dx dp, dx dp times p times 10 to the negative fifth times 3 x squared plus 10 to the negative second is equal to negative 10 to the negative fifth x cubed plus 10 to the negative second x plus 1. And of course, finally, to solve for dx dt, we divide both sides by p times this polynomial, right? That's a lot of work. I'm going to go ahead and admit that. There's a lot of work here. Looking at how they went about this, notice they did something slightly different. They divided both sides by p and multiplied both sides by that polynomial. And what that allowed them to do was to shrink some of the math. Right away, they get everything in terms of dx dp, right? Each of their terms have dx dp, and it's equal to 3 over p squared, the negative of that. So you can factor out the dx dt and solve for it directly. Then you come in and you say, all right, well, the problem wanted to know what dx dp was when x is equal to 100. So we need to know what p is when x is equal to 100, because our derivative is in terms of p and x. So plug in 100 into our original equation, and we get p as $1. So we can plug in 1 here and 100 here to solve our problem. Excuse me. When we do that, we get that our answer is negative 75 when x is equal to 100. Holy hell, that was a lot of work. But again, notice that they went about it a slightly different way that reduced the legwork. The point here is to show that there is, excuse the macabre expression, more than one way to skin a cat. That we can go about it in slightly easier ways if we see them. Had I seen this, I probably would have taken that approach right away. I didn't. Looks like I've got a question, so give me just a second. Okay, cool. Now we're at the end of that section. Getting into section 2.8. Again, this is the week 5.2 notes. I have no clue what slides these are. Week 5.2, page 64. Section 2.8. If I can get that thing out of the way. All right, there you go. So now we want to start finding related rates. Now we want to start finding things like a common example. I get this totally erased. Now we want to solve problems like this. You got a cone. You're filling it full of water. Right? Filling this thing full of water. You know the rate at which the faucet is pouring water out at. You know how height changes with respect to volume. What you want to solve for is how the height of the fluid inside your cone changes with respect to time. Excuse me. This is a really common problem. all you know is dv dt, dh dv. But what you want to find is dh dt. Another common example of this type of problem you've got a ladder up against a wall. You know how fast down it's moving. You want to solve how fast out it's moving. So let's say this ladder is sliding down the side of the wall. You want to know how fast it's being kicked out. Another example might be something like you've got a street light. Somebody walking away at some speed. So they're casting a shadow. You want to know how fast that shadow shrinks, expands, moves away, whatever, right? There's all sorts of different similar problems that we're going to go over here. And they all use related rates and this idea of chain rule and implicit differentiation, like we just talked about. So notice what we've got going on here. We're told that y and 2x are equal, right? So we know that y is related to x as 2 times x. So if y changes with respect to time in a particular way, then we know the derivative of y with respect to time has to be equal to 2 times the derivative of x with respect to time. These rates then must be related in some way, and this is all we're going to be doing. So, for example, we're given this problem, y is equal to x squared plus 3. What we want to find is dy dt when x is equal to 1. We're going to have to apply an implicit derivative to both sides. We're going to have to apply the derivative with respect to t to both sides. So we're going to get d dt of y is equal to d dt of x squared plus 3. Well, from that last section, we just saw this thing's going to come out to be dy dt is equal to d dx of x squared times dx dt. Okay. Well, if that's the case, then dy dt this thing has to be equal to 2x dx dt. Well, we know x here has to be equal to 1, because that's what we're asked to solve for. But we're also given that when x is equal to 1, dx dt is equal to 2. So dx dt is also equal to 2. Plugging all of that in, we know that dy dt is equal to 2 times 1 times 2. Or just 4, right? So checking it out now. Here, we're applying an implicit, we're using the chain rule and implicitly defining dy dt, dx dt, right? This is how the chain rule gets applied here. But we know how dx dt behaves when x is equal to 1. We're told that. So we can plug in 2 and we can plug in 1 to solve for dy dt. So given that we know y and that we know dx dt when x is equal to 1, we can find dy dt based on the chain rule. Having said that, let's take another quick break. Well, let's not. It's been like, what, 10 minutes almost? Let's not take another quick break. Let's just go ahead and do this problem, and then we'll take a break. So this problem wants to know something about the ripples of a pond or pool after you drop a pebble in. So we've got some lake. We drop a pebble in, and we get these waves, right? Let's pretend I can actually draw waves. It'll look something like this, right? These waves are going to move out. So we know that the radius of the ripple is increasing at a constant rate of 1 foot per second. So dr dt is equal to 1 foot per second. What we want to find what dA dt is at radius equal to 4. So this is what we're told, that the change in radius with respect to time is 1 foot per second. And what we want to find is what the change in area is with respect to time when the radius is equal to 4 feet. All right, we're going to start thinking about other things we know. How can we relate radius to area? Well, in this case, a ripple is thought to be a concentric circle, right? So we've got this picture going on. And we want to find the entire area inside, how that area changes. Well, we know that the area then is equal to pi r squared, right? Okay, well, we want dA dt when our radius is equal to 4 feet. We know the change in radius with respect to time is equal to 1. It's just a constant. So given that, since we know area is equal to pi r squared, let's go ahead and differentiate both sides with respect to time. d dt of A is equal to pi times d dt of r squared. Well, the left-hand side here, this thing's going to become dA dt. The right-hand side, we're going to have to apply implicit differentiation, right? Excuse me, or the chain rule, however you want to think of it. So this is going to be pi times d dr of r squared times dr dt. So this is going to come out then to be dA dt is equal to pi times 2r times dr dt. Well, we know dr dt is equal to 1. So dA dt is equal to pi times 2r. We know that r is equal to 4, so dA dt at r equal to 4 is going to be pi times 8. Now let's check everything. So we start with the fact that we know how area corresponds to the radius. And we're given how the change in radius corresponds to time. And what we want is the change in area with respect to time. Okay. So we go through, set up our equation. Cool. We know that area is equal to pi r squared. Differentiate both sides with respect to time. We get the change in area with respect to time is equal to 2 pi r dr dt. Well, dr dt we know is 1. And we're solving for when r is equal to 4. So plugging all of that in, you're going to get 8 pi. Bada bing, bada boom. That's it. So having said that, just some quick guidelines for how to solve these problems. I'm going to let y'all read these on your own, because after we go through a couple more of these problems, I think you all will see the trend. So in this next example, we've got a balloon that we're pumping up. We want to find the change in radius with respect to time. And that is when the radius is equal to 2 inches. So we're pumping, go back. We're pumping up this balloon. The volume's going to change. We want to know what the rate of change of the radius is when the radius is equal to 2. And we're told that we're pumping this up at a rate of 4.5 cubic inches per minute. So that is dV dt. I'll write all of this on the board now. What is dr dt at r equal to 2 and we are given here dV dt is equal to 4.5 cubic inches per second. All right, so what we're going to need to do is start by setting up a relationship between volume and radius. Luckily, the balloon's supposed to be spherical, so we can just use the equation of a sphere. The equation of a sphere tells us that volume is equal to 4/3 pi r cubed. If you don't have that memorized off the top of your head, don't feel bad, neither do I. I have to derive that every time I need it. It's just not something that I've memorized anymore. So now we need to apply the derivative with respect to time to both sides. Tra-la-la-la-la. Erasing this board and rambling to fill in the dead air, dead space, whatever. We are, like I said, going to apply the derivative with respect to time to both sides of this equation. When we do that, we get dV dt is equal to, well, 4/3 times pi, that's a constant. So let's pull that out to get dV dt is equal to 4/3 times pi times d dt of r cubed. Chain rule. Chain rule and implicit differentiation. This is going to give us dV dt is equal to 4/3 pi times d dr of r cubed times dr dt. This is going to become 3r squared, right? And that's going to stay dr dt. So we get that dV dt is equal to 4 over 3 times pi times 3r squared dr dt. We want to solve for dr dt, so we're just going to divide everything else from both sides, right? Dividing everything from both sides, we get dv dt times 3 over 4 times pi times 3 times r squared, the negative first power, is equal to dr dt. We can simplify this a little bit to get dv dt times 4 pi r squared in the denominator is equal to dr dt. Well, we know dv dt and we know r. So now we can plug those in and solve for dr dt. And find out how fast the radius of this balloon changes with respect to time. Cool? So looking at the rest of this problem, notice they start by setting up the same set of relations, right? Say, all right, we know the equation for volume with respect to radius. We're given how dv dt changes, or what dv dt is. We want to find dr dt when r is equal to 2. So going through, we have volume. We're going to go ahead and differentiate both sides. We're going to get that same equation that we got on the board. And we're going to divide both sides by this term, right? To solve for dr dt, I mean by this factor. To get dr dt. Then, now that we're here, we're going to plug in r is equal to 2 and dv dt is equal to 4.5 to solve for this. And we find that the radius with respect to time changes at approximately 0.09 inches per minute. And I think that's because up top, yep, it's not per seconds, it is per minute. I miswrote this here. So it doesn't change very fast at that point. Having said that, let's go ahead and take a 10-minute break. Come back at 8:30, and we'll run through another few problems.